as well. There we go. All right. So first order of business, welcome everybody. Happy Tuesday to you. I know it's Tuesday because I had to put the garbage out this morning. That's my anchor point for where we are in a week cycle. I also did some updates to the syllabus, as I mentioned in an email. So just to make sure that we're all on the same page, I updated the printable version of the syllabus here. So this has all of the changes that I've made to the structure, to the assignments and due dates and whatnot. Pertinent thing to note, I bumped your next formative assessment back a week, so you have nothing due next week. Nothing at all. Have a breather. Catch up on the rest of your life. And then we'll have a formative assessment and homework 3. Homework 3 is going to be covering polynomial models of change, so the material that we're going to start today. I'm expecting that to take about 3 classes, which means that you should have at least a week or 2 before that assignment is due based on the schedule. In addition to that change, I've also changed the deadline for work completed on finals week to be 5 p.m. So I need to be able to turn in grades earlier than I had thought, which means I can't wait till midnight. So if you can get everything to me in finals week by 5 p.m., that would make me very happy. That week we are not having class, but I am going to have office hours during all of the time that I would normally be teaching. That way, if anybody needs help, there should be plenty of opportunity for me to work with you and make sure that everybody can get everything turned in on time. Okay, any questions on schedule stuff? No? All right, then answer key for formative assessment number 3 I posted this morning. That way we can go over it. You can see what I thought I would write down in the boxes, and we can talk about why things are correct or not correct that you wrote down. I had a look at everyone's assignments this morning. A lot of variability, I think, in how folks are doing with the material. I will say that all of those terms on the formative assessment were defined in lecture 5. So the first half of it, walking you through the empty model to the fixed linear time model to the random linear time model, that's the material that I was hoping to get you to review with this assignment. Let me find that document. So this is the answer key that I posted a few hours ago as to what I meant for matching terminology, notation, and models. So in terms of the synonyms, terms that are fixed effects, so words that you should associate with fixed effects are terms that belong in the model for the means, at least in this class. It's referred to as the structural model in other places. It is also, you can think of it as estimated constants. So the term fixed means everybody gets the same. It is literally one number that describes an intercept or a slope, and everybody gets that same one number as applied to their creating their predicted outcome. So fixed effects are constants. Terms that have level 2 variances and their interpretation. Here are the terms that I thought of. So in the context of longitudinal data, level 2 is between person. So multi-level models are used for all kinds of data structures. You can always associate the labels between and within with level 2 and level 1 respectively. So level 2 is always between something. Level 1 is always within something. What that something is depends on the design. So in our case, because we have occasions that are modeled as nested within persons, level 2 is person, so between person. Level 1 is time, so within person over time. And so I put down here terms that have level 2 variances. Synonyms for those variances are going to be between person differences, inter-individual differences. Time invariant will be the types of predictors that go in that level. And also random effects. So the names of the variances at level 2, those are random effects variances. Intercepts and slopes being 2 particular kinds of random effects. And they live in the G matrix. So any others that you thought of that I should add to this list?
Model of the variance.
Yeah, model for the variance would be, say, both of these, because we have level 1 variances and level 2 variances. Yep, I'll take that. I just thought of another one myself. Macro. as opposed to micro. That works for this context. That's more common in clustered designs, but it's still appropriate. Any others? Okay. And then within person, level 1, so variation that is within persons over time, I added intra-individual residuals. So we're talking about residual variances and covariances, and those live in the R matrix. You could also add longitudinal or micro to that list. Others that you can think of. All right. So then first model, I'm going to go down a column. So the first model here, this is an empty model for single level data. So going back to the simplest possible model you would have for data in which you have an outcome from one outcome per person, and therefore you have one residual per person. In this model, the only fixed effect is beta 0, which is the fixed intercept. Intercept is always the expected outcome when your predictors are 0. In this context, without predictors, it's just the expected outcome, which is the mean. So beta 0 would be the mean of the outcome. E sub I put in the level 2 box. However, I think that it would be correct either way. So I have a note that it also could have gone down here. My rationale for putting it here is that if you only have one E per person, the variation across the E's is person level variation. So even though it's a single level model, conceptually E in this context is the differences between people. So E is a residual. The variance of the E residuals across persons is known as residual variance in a regression context, but it does represent between person differences. But I saw people also put it down here because it was the level 1, meaning it's only one level, so E is the lowest level residual. I'll take that as well. Okay, then the next one, empty means random intercept model. So I call this empty means. A synonym for this, by the way, is unconditional means. You'll see that word as well. That's a Singer and Willett term. And this one is trickier. A number of you made the same mistake across all 3 of these models. The betas. The betas are not parameters. They are not fixed effects. They do not have variances. The betas are placeholders. The betas are simply containers that hold the fixed and random effects that pertain to the same idea. So beta 0 is a container for how each person gets their own intercept. Beta 1 is going to be a container for how each person gets their own linear time slopes. So if you had betas anywhere in the list below here, they don't go in here. You can write the same model without the betas if you just put the gammas and the u's directly into a single level equation, and that then should hopefully indicate that the betas are not estimated parameters. Okay, what are estimated parameters? The gammas. Gammas are fixed effects. So there's one fixed effect in the empty means model. There are 2 fixed effects once you add fixed linear time, and there remain 2 fixed effects in random linear time. So I was looking for you to recognize what the fixed effects are in each model, but also how they change interpretation as terms are added. So not everybody gave the interpretations. I would encourage you to go back through your own work and add those if you can, because this is the fixed intercept, gamma 0, 0. But what it means depends on what else is in the rest of the model. Okay, so yes, betas are placeholders. Betas are not estimated parameters. So in the context of an empty model, if you have no predictors, the fixed intercept is just the grand mean. But it requires one more layer of interpretation because of the random intercept. More technically, gamma 0, 0 as the fixed intercept is the mean of the person means. That is a distinction that only matters if you have unbalanced data. So if you have different numbers of occasions per person, then you will not get the same answer if you just take the mean of the entire column versus if you take the mean of each person's data and then take the mean of those means. So it's an order of operations thing. Technically speaking, gamma 0, 0 is the mean of the person means. So you can get a different estimate for it if you have a random intercept in the model than if you don't. The same thing is true of the slopes, as we'll see in just a moment. Okay, questions so far? So we're right here. So if gamma 0, 0 is the fixed intercept, terms that will have level 2 variances. So u sub 0 I, the random intercept. So u sub 0 I is a term that applies to each individual. It is not a variance. It has a variance. So in terms of notation, it is not correct to say that u0 is the random intercept variance. u0 is a random intercept. Its variance is denoted with tau squared. So u is the idea that each person needs their own intercept. What the model then estimates is the variance across the u0s as one number, which is tau squared sub u0. So in this model, u is the random intercept, and what that means is that it is the deviation of each person's mean from the mean of the means. So there's no time in the model at this point. So we're not talking about time 0 or anything. An intercept is just a mean at this point. So u0 is how far off a person's mean is from the mean of the means, from the fixed intercept. If you put gamma 0, 0 and u0 back together again, that's the idea of an individual intercept. But beta 0 is not a thing. It just holds that idea of an intercept together. E, which it looks like I dropped a T subscript on there. By the way, I wanted to teach you this. Let me answer the question and then I'll talk about subscripts. So you will estimate a number for the gammas but not for the u's. Correct. Correct. Gamma is a fixed effect. That means you get a number as the best guess for what that fixed effect is going to be, and you get a standard error that goes along with that estimate. So fixed means you care about that particular instance. Random means you don't care about each instance, you care about the variance across instances. So if you had u0 as a fixed effect instead, then you would have a u0 for person 1, a u0 for person 2, and that is a different model. That's a fixed effects model, as is more common in econometrics and in other contexts, political science, public health, sometimes sociology, like some of those fields tend to use fixed effects models, and it's a thing to test whether or not you should have fixed or random effects. Fixed effects don't allow you to predict variances, but random effects do. So yes, good question. Okay, so the notation here. There are two different ways to make notation in word processing, PowerPoint, etc. I will show you one of them. So if I type in E here, if you hold the control and the shift and the equals, that's superscript. If you do just control and equals, that's subscript. So you don't have to go hunting through the menus to find subscripts and superscripts. So it's control equals to get to a subscript, and then control shift equals to get to a superscript, and then if you hit it again, it goes back to regular. The other way that you can do it is with the equation editor, and that is Alt and equal, and it pops up a thing that looks like this. So if I type E in here, note that it automatically italicizes certain things. And then if I type underscore and then TI and then spacebar, it automatically converts it into subscripts. Likewise, if I wanted to type a beta inside the equation editor, I hit a slash and then lowercase beta, and then if I hit the spacebar, it becomes the character. The alternative, if you wanted to do it outside the equation editor, let me get rid of this for just a second, is to find the symbols menu and then hunt for it. So the ones that I've used most recently are down here. It can take a while. There's beta, insert, close, and there now I've got a beta. So it can be easier to use the equation editor because then you don't have to hunt for all the symbols, but it also requires more memory and it makes your files bigger. But it uses the same language that you can use in LaTeX and in other places to write your equations more quickly. So just as an FYI on those. So it should be ETI, correcting my own typo here. So going down into the subscript, ETI there, and ETI there. Nope, not. Come back. There we go. That looks better. Okay. Any questions before we go to the next model? ETI is a time-specific residual. Yeah, the simple thing. It's one of those things that makes your paper look very unprofessional if you don't use the symbols and the subscripts correctly. So if you're going to have equations, you got to do it right. I would say don't do it at all if you're not going to use equations and subscripts and things properly. Which, to do it in text versus equations, some journals have a preference. So for instance, when I was writing my book, they insisted that I use the program math type. They would not let me use the equation editor in Word, and that was a whole thing. So journals will have preferences as to how you write your equations in terms of what to do so. All right, so next model then, fixed linear time random intercept. The difference between the models is right here. We have picked up a fixed time slope, and that is the change in y for a 1 unit change in time. And that is a slope that applies equally to everybody. So at this point in the model, we are assuming parallel linear change. Because we have time in as a predictor, the fixed intercept changes interpretation. It is no longer the mean of the person means. Now it is the predicted outcome at time 0 specifically. So you always want to make sure that time 0 is within the span of your data so that the intercept makes sense. U0, though, has the same interpretation because on the random side, U0 is still the only random effect. So you can still think of U0 as how far off your person's mean is from the grand mean because they're parallel lines. So if you have parallel lines, you can have the same U0 here as you have here as you have here. So you can think of it as at time 0 or the mean because it would be the same number either way. And then E residual has the same interpretation in each case. Last but not least, adding random time slope. The only change to the fixed effects is to condition the fixed slope to be the mean of the person's slopes. So in the same way that the fixed intercept was the mean of the person means once we have a random intercept in the model, the fixed time slope is the mean slope across people. And U1 then is how far off each person's slope is from that fixed mean slope. This matters to the extent that you have different numbers of observations and different time values across persons. The mean slope will not just be the slope of the whole column in that case. Then in the level 2 section, U1 is now another random effect that gets a variance. So U1 is the deviation of the person slope from the sample mean of the person slopes, and it has a variance tau squared sub u sub 1, and not shown in the equation, but as part of the estimation, we also estimate a covariance between these two u's, because where you start is probably going to be related to how you change. And then E has the same interpretation. So E is the same across the board. The only thing that changes is what E is relative to. If you have an empty means random intercept model, that is a series of parallel flat lines. E is relative to that trajectory. If you have a fixed linear time random intercept model, E is relative to a series of not flat but still parallel lines. Once you have a random linear time model, E is relative to a series of trajectories with different intercepts and different slopes. So E should be reduced across models. The variance of the E's should be reduced as a function of either being explained by fixed linear time or having the U1 random time slope partitioned out of it as a further source of person dependency. Okay. Questions?
What does the covariance between the intercept and slope actually tell you?
It doesn't change the predicted outcome any, but it does tell you the extent to which people who start out higher change faster or change slower. It's a function of where time zero is, as we will learn in this unit. So it reflects not only the correlation of the intercept and the slope, but more specifically the intercept at time zero. So if time zero is at the beginning, then it's the correlation of initial status and rate of change. If time zero is at the end, it's the correlation between ending status and rate of change. So it's something that we always include. It may or may not be of interest, but it just makes sense conceptually that if you're allowing a person to have two random variables, they probably should be related because they came from the same person. Okay, other questions? No? We're feeling okay about this? Ish? I'm seeing a lot of like, not really, but I don't want to say so in front of everybody. Well, the good news is that in our new unit, the first thing we're going to do is do all of this one more time. How's that sound? Repetition. The next unit is about nonlinear change, but to get to nonlinear change, we got to go through linear change. So you will get a chance to practice all of this notation and concepts again. So I think what I want to do with this is sort of go back and forth between lecture 6 and the examples. So talk about a set of models, then show the code, then talk about some more models, then show the code. I think that will hopefully keep it from being more overwhelming. So I originally had one handout for all of the example models that go with this lecture, and it was 57 pages long. I'm not even kidding. That's not hyperbole. And I thought, you know what, Lise, that's a lot. 57 pages for one handout is a lot. So I carved it up into 4. So example 6a is about polynomial models of change. That's going to be your next homework. The set after that, which is doing piecewise linear slopes of change, is going to be the next homework after that. And then the last 2, it's going to be exponential models of change and log time versions. You won't have a homework over, I don't think, but we will see. So this is to say this will take a while to kind of unfold. All right, are you ready to do this? So we're starting with lecture 6 and example 6a. So big picture stuff and then diving into ways of examining nonlinear change. So here's the example data that we're going to be playing with through all 57 pages of this handout. It is real data. So I got permission to use it. This is the same data that was featured in example 3b. So it is 6 sessions of older adults' performance in a measure of processing speed. So this is called number match 3. It's a task in which there are 3 numbers above a line on a computer screen, and there are 3 numbers below the line. And your task is to say whether it's the same 3 numbers as quickly as you can. So a fairly low-level processing task. It's something that you would expect people to get better at with practice. That was the whole point of the study, was to examine the extent to which these older adults showed improvement in a task over a 2-week period. So these are 6 sessions of practice with this task. I forget how many trials we're in with each, but so we're modeling the mean response time for each session as the outcome for each adult, and expecting to see some sort of practice curve where initially the decline in performance is greater, but then they kind of start to level off. So this picture, what's known colloquially as a spaghetti plot, and what is known more formally as a plot of individual trajectories, shows you the data. So this is kind of messy. It's hard to see what's going on. You can kind of see there tends to be, decline at first, but certainly not. I don't know what happened with this person. Apparently they hated this task or they got worse. They were having an off day. But this is real data. One thing to keep in mind is that the scale of this response is response time in milliseconds. That actually is going to cause some problems across software programs in getting the numbers to match because it's such a weird scale. When I tried to estimate these models in M+ for the book, I had to convert it to response time divided by 100 to get it to even work. So it's a little bit of a strange outcome. The numbers are going to be very big because it's in milliseconds, but keep in mind that smaller is better. So if people are improving in performance, they should have lower response times. So these are the data. So first things first, what kind of change do you think we would have based on the theoretical properties of the context and the design of the study? So I have time here in quotes because in certain circumstances, what time should be is actually a question that you'll have to answer. In this context, there is no question what time is, it's session, because there's no natural maturation or developmental process. Elder adults are not aging within a 2-week span, right? The only reason why response times would change is exposure to this test, and that's it. So time is like, I know what that is in this context. In chapter 10 of my book, I talk about other situations in which this is an open question. So for instance, if you have data from children, you could think about certain outcomes being a function of biological age, right? Whether you have a 3-year-old or a 3.5-year-old or a 4-year-old, I've come to learn that there is a big difference between a 3.5-year-old and a 4-year-old, right? I never would have thought that before, but it's true. Or you could think of it as, are you in preschool? Are you in kindergarten? Are you in first grade? Right? In kindergarten, you could have anywhere from a 4-year-old to a 6-year-old all at the same time if time is great. So in certain types of designs, you may have to think about this in a way that is motivated by the process you're studying and what you would expect theoretically. Is it age graded? Is it, scholastic? Is it a combination of both? We're sort of sidestepping all of that just to keep this relatively straightforward. So the example of time that I'm using in this unit is completely within persons. There are no between person differences in time. That greatly simplifies the models because I know that time is only a level 1 predictor. It only has level 1 within person variance, which means its fixed effects can only be level 1 effects. If time had between person variance as well, I'd need another predictor in the level 2 model to address that. So this is a simplification because looking at nonlinear change is already hard enough. So from there, you have to ask yourself what kind of theoretical process would have driven change and what would that look like? Is it continuous or is it something more discontinuous? The latter is particularly useful in studies where you have different phases. So like multiple baseline kinds of trials where you have people do something for a period of time and then you change the instructions or the situation and they do something again. Like that kind of time where you're changing what happens, like that's a discontinuous type of design. Whereas something like this, sessions 1 to 6, I expect people get better. I think if change is happening sort of continuously. I do think it's going to be nonlinear. I think that the extent to which people improve is going to slow down as they get more practice, and eventually, in theory, they should asymptote at some level of optimal performance. So there's many different options for modeling change. Which family of models is going to be right for you depends on your data and the context. I'm going to show you the same data a bunch of different ways just so that you get a sense of what's out there and how you can choose between them and maybe combine them to measure change in the most appropriate way for your design. So there's lots and lots and lots of choices is what I'm saying. So baseline models. Going back to Your first homework assignment, for instance, in which there were only two kinds of means models, empty or saturated. So on the model for the mean side with respect to time, these are the two baselines for worst and best. An empty model is when you have only a fixed intercept. So that's what I call an empty means model or an unconditional means model. That says there is no change. So that is like the simplest model you can possibly have. The role of the fixed intercept is to allow your outcome mean to be different than 0, but it doesn't change over time. That model is always possible. It only has one fixed effect. On the other end of the spectrum is what I call the saturated means model, what other people call too, and what is also known as analysis of variance. So the idea that time is treated as a grouping variable, and you would estimate number of occasion minus 1 slopes that would fully saturate the means. It is the best you can do. It's only possible to estimate a saturated means model when you have balanced data. So everybody has to have the same set of possible occasions for this to be identified. If you're in a situation where you don't have balanced data, I would often recommend that you round time into some kind of convenient interval just to estimate this model to make a picture. Not to like distort your data in an analysis, but just to get a heuristic, because this gives you the right answer for what your trajectory needs to look like. Because people don't have hypotheses in longitudinal studies about what happened from time 1 to time 2, what happened from 2 to 3, what happened from 3 to 4. They want to talk about growth or decline or maturation, right? It's implying some kind of function. So the object of the game is to figure out what kind of function goes through the means, and thus what kind of fixed effects related to time do we need to capture that function. So the choices then, the 57 pages of handout, talk about polynomial slopes, piecewise slopes, and truly nonlinear models by which to name this trajectory. So what I will show you next then is the results for that data set we're going to be working with for these two models. And then we'll look at this in SAS as well. So the red line is the prediction from the empty means model. If I take that 6 occasion data set, I run it through my software and estimate just a fixed intercept, it works out to be about 1770 milliseconds. So on average across time, it takes people about 1.7 seconds to do each of these trials. That's one baseline. That's the worst possible baseline. Because I have balanced data, because everybody shares the same 6 sessions, I can also estimate the saturated means Anova model, and that returns a function that looks like this. So the mean at the first occasion is just shy of 2 seconds. The mean at the last occasion is about 1700, a little under 1700 milliseconds. And then we have this function. So what do you think this looks like? Do you think this looks linear or non-linear? Yeah. Thumbs up for linear, thumbs down for non-linear. Yeah, I could draw a line through it. The line's not going to fit very well. But I don't know what kind of non-linear this is. So what we're going to explore are different ways of capturing this trend across the means. The role of the fixed effects in these models is to capture this pattern. So we can put fixed effects in, and I will teach you how to compare it to the right answer given by this trajectory to see which patterns appropriately capture the means. So first glance, I'd say this looks sort of quadratic-y. It looks like half of a U to me. So that's polynomials is where we're going to start first. Okay, so saturated means is the answer key for what the fixed effects related to time have to do. With me so far? Okay, so the red is meant to be a tie-in to model for the means fixed effects, but we got a whole other side of the model, right? What am I forgetting so far? When I say other side of the model, this is Lisa's talk for what type of idea? B. Yeah, model for the variance. all of the E residuals around this trend, right? We got to talk about what happens to the variances and covariances over time as well. So on that side of the model, we are trying to figure out which aspects of change show individual differences. So which fixed effects need variances around them to allow each person their own intercept, their own slope, their own nonlinear slopes. So we want to make sure that we have time zero someplace that's meaningful to us, and estimate random slope variances. And while that is interesting in and of itself in answering the question, do people change differently? Behind the scenes, it also is going to imply a particular pattern for what the variances and covariances look like over time. So the same idea of simplest possible model to most complex model on the variance side. We have compound symmetry as the simplest possible model that would apply to longitudinal data. We have unstructured as the most complicated model. So now we're not talking about the means over time. We're talking about all of the error around the means over time. Error/individual differences. You say tomato, I say tomato. So compound symmetry is one pattern. This is otherwise known as the univariate approach to repeated measures Anova when estimated in least squares. We also would call this a random intercept only model. This model for the variance that creates this structure has two terms in it: a level 2 random intercept variance and a level 1 residual variance. Those two terms sum together to create a total variance on the diagonal that stays the same over time. The level 2 random intercept variance, so the amount of variation due to mean differences, forms the covariance over time, and it does so equally across time. So compound symmetry has a 2-parameter model for the variance that specifies equal change. That's the only way that you can have the variances stay the same over time and have the covariances stay the same over time as if you have parallel lines. This is skinny jeans, by the way, from about a month ago. We were trying to draw parallels to real life. Unstructured was sweatpants. It always fits. Unstructured is the right answer. It is a structure that has no pattern. It says K, let the variance at time 1 be whatever it wants, let the variance at time 2 be whatever it wants, time 3 whatever it wants, time 4 whatever it wants. Let all the covariances be whatever they want. Fits perfectly. We're not trying to simplify the pattern, we're just letting it be. Now this is a great idea, except for 2 reasons. When is this not possible? 2 situations I'm thinking of in which we don't have the right answer available to us. Small sample size, yep. At a minimum, we need as many people as we have parameters in this thing. Yeah, so small sample size in relation to the number of parameters to be estimated, yep, that's one. Unbalanced data, yes, that's the other. I don't have a row for time 1.5, time 2.2, time 3.1. So unstructured is not possible whenever you can't summarize everybody's data with the same matrix. Can't do it. So this idea of unstructured is the same idea as a saturated model in SEM world with respect to the variance side. And in theory, once you can have this unstructured model, then you can test absolute fit of anything that happens in between. And so I will show you how to do that within this context, which is common in SEM, can be done in MLM as well, so long as you've got unstructured. So if you're in a situation in which you don't have enough people and or you have unbalanced time, you kind of don't know where you're headed. You can start with compound symmetry and you can add things to model to see if it gets better and better and better, but there's no endpoint. So unfortunately, I don't have any great advice for you because to the best of my knowledge, the field hasn't really figured out how to solve this problem. They just ignore it. So if you have a situation in which unstructured is not possible, you're kind of stabbing in the dark as to whether your model is good enough. All you can do is add things and see if you can make it better. So the situations in the middle, this is where we have the alternative covariance structure models. So maybe a random intercept plus an auto AR1 residual correlation, a Topolitz, random intercepts plus random linear time slopes. All of those things are options that are in the middle that are hopefully going to mimic unstructured, but do so in a way that uses fewer parameters. So here's the fit of those two baseline models to our example data. The blue line. So the y-axis of this plot is the total variance and the x-axis is occasion. So this is not the means, this is the variance. The blue line is the predicted variance in total, marginal in V, for each occasion from a compound symmetry model. So the distance up to this blue line is partly U0 variance and partly E. The blue line is the sum of the two. So what was on this diagonal right here. So the random intercept only model predicts the variance is the same across time. Here's the variance that was estimated on the diagonal of the unstructured model. So again, this diagonal right here, that idea, for 6 occasions in our data. Does it look like the variance stays the same across time? Does that black line look flat to you? I don't think so either. Now note that I had to cheat the axis because the variance is on such a large scale, but yeah, it looks like there is more variability at the first occasion than there is at the last occasion. In other words, as people do this task, let me get my arms to go the right way. There we go. They're becoming homogeneous. Differences between people are reduced the longer this practice sessions go on. So I need something that predicts that the variance should decline over time, and that is what the random slopes for time are going to be for. Each model that we're going to examine says that the variance should change over time in a different pattern. So we'll see which one fits best. But this is the right answer. We also have all the different covariances that are going to be changing over time, and the random slopes for time are going to predict those as well. So I could have made more plots than this, but this is the general idea just for variances. Covariances are also something that we'll have to pay attention to. So in summary, we have 2 jobs to do in figuring out what our best fit model for change needs. So this is a process of establishing what is known as an unconditional model for time or an unconditional model for change, meaning we got to get all our ducks in a row with respect to time first. Then we tackle the other predictors that we care about, but time has to come first. So in fitting these models, we need to worry about the model for the means. What fixed effects do we need to capture the average trajectory? So what is the pattern of change of the means over time, and what fixed effects related to time are going to capture that pattern? On the other side then, simultaneously but separately, the model for the variance. Which random effects do we need to accurately capture how the variances and covariances change across occasions? If I only have a random intercept, that says they stay the same. Doesn't look like that's going to work here. I need some other random stuff. So which fixed effects that describe the overall trajectory of time, which of those show individual differences? That's what we need to know. And those individual differences in turn imply variance that changes over time. All right. Let's do, here's a slide that I think will be relevant later. It's extra things that I'm going to show you that's not in the book. How to test whether or not your model is adequate when you're using REML instead of EML. And not Rambo, Mr. Translator, or REMO, R-E-M-L. That's what I'm talking about. All right. So let me pull up then example 6a and walk through the steps by which I generated those pictures. So trying to map the big ideas of baseline models to how this actually happens in practice. So example 6a is what I've got here. First step is always import your data. So these are the same data featured in chapter 6, number match 3 response time across 6 sessions. All of the files are available for download for all 3 programs, except for the nonlinear models, the truly nonlinear models, I should say. So in terms of creating new variables to do this analysis, there's really only one that we need for today. We need a predictor for time that is going to be treated as a quantitative predictor. So do you remember in the previous unit we had time and we had wave, and in your homework you had time and then you had week? Well, in this case we have session, which is the categorical ID variable for time, and then I'm creating a new predictor that's time 1, which is 1 is where time is centered. So that's why I have the 1 there, to be consistent with how I typically name predictors. So time 1 is session minus 1. So session is going to be used as an ID variable. It's being treated as categorical. Time is going to be treated as the quantitative predictor that we give slopes to. And this is going to be the basis of how we check whether or not our trajectory implied by the fixed effects is good enough. So I'll save that for when it's relevant. Stata folks, you are doing the same thing, but with one new fun twist. I could not figure out how to make Stata use a variable multiplied by itself in a random line. So I gave up and I made the squared term. So there may be a way to do it, but I couldn't make it work. So I have time 1 and then I have time 1 SQ, which to me is squared. So I made an observed variable for what is going to become quadratic time in these examples. And the demicodes to be explained later. And then folks using R, I've got the typical setup here where I'm defining a variable for the path name, the file name, reading in the SAS dataset. I'm creating one new variable for session in which the 6th session is the reference so that I can get the same results across programs. And then I am creating time 1 as a predictor from session minus 1. In R, I figured out a way to make the quadratic without having to make a new variable, so I don't have to make that for this. And then the codes to be explained later. Okay, any questions on the setup for the story? Okay, then first stop, let's get the best. So the answer key. On the mean side, saturated means. On the variance side, unstructured. I've got 101 people and only 6 occasions. I can do this. So I will. So this model is being estimated for descriptive purposes. I want to know what the trajectory should look like if I let each mean be whatever it wants. I want to know what the variance would look like at each occasion if I let it be whatever it wants. And all the covariances get to be whatever it wants also. So the way that I'm doing that is taking the session variable that is on the class statement and putting it in the model. So I am not estimating a slope. I have 6 occasions. How many slopes am I estimating by doing this? Session is being treated as a categorical grouping variable. I have 6 occasions. How many slopes am I asking for? Yeah, 5. Okay, so this is not at all obvious, which is why I'm making it a point, because I have answered this particular error message so many times. Not you guys, but in life, right? All the people that I've taught this stuff to before, this has been a point of contention because it's confusing and it differs across programs. But because session is on the class statement, that is why I'm getting 5 slopes. So I have denoted session as a grouping variable by putting it on class. In Stata by saying I be last. I means categorical, B last means make the last one the baseline. And in R by saying that session is a factor variable. So all of those things, class in SAS, I dot in Stata, and factor in R. And you can add to this list if you use SPSS, if you put it in the fixed factors box under the windows, or if you use it on the by statement in SPSS syntax, that does the same thing. Every software package that I know of has a way of denoting a predictor as categorical, and it will automatically create dummy codes and estimate slopes for those dummy codes. The exception is M+, by the way. So because I'm using that version of the variable in the model line, I am getting 5 slopes. I get 1 intercept, which is going to be for session 6, and I get 5 slopes. Perfectly saturates the means. Because I have it on the model statement, I can ask for those means. So LS means then recomputes using those 5 slopes what the predicted mean is at each occasion. Diff equals all gives me all possible pairwise comparisons. In Stata, contrast is used to give me an F test for the mean differences across time. That's not a default. Margins gives me the means, and PW compare on the margins gives me the pairwise mean differences. And in R, the saga continues because no one has answered my query as to how to make R do everything I want out of one model. It's still a saga. So I'm back to using GLS because that's the only package that I've found that allows R matrix structures in the absence of random effects. So we're back to GLS, which has the unfortunate consequence of choking on Satterthwaite degrees of freedom in every data set that I've tried. So this is not the right results out of R, but it's the best I could get them to match. And in anticipating your homework, I will not ask you to do a model that all the programs can't do, okay? I will spare you this agony of trying to match everything across outputs. But I've got GLS. The model statement then has the factor line for the session. Correlation, core sim as numeric session means estimate all possible correlations across occasions. And then this chunk right here adds heterogeneous variances across occasions. So unstructured in GLS takes a hell of a lot of code, but at least it's built in. And then EM means was supposed to give me the means and the mean differences, and it threw up about Satterthwaite degrees of freedom. So then I had to go to LS means and do residual degrees of freedom, which is incorrect. And then I figured out how to get the right F test using Anova. So now you're starting to see why this takes 57 pages. So here's the right answer. So in this model, we have no random effects. So R is V. R is marginal. So 301,985, that's the variance at session 1 in response time, period. Not predicted, not partitioned into levels, just period. 259,150 is the variance in response time at session 2, and so on. And so that is the data that I used to make this black line right here on slide 8. So I just plotted those 6 numbers for you. Covariances are hard to tell what they imply because they're a function of variance, and so that's why the correlation version of that same matrix is useful. And you can see to what extent the session response times at the first occasion are related to those at the second occasion, the third occasion, the fourth occasion, and so forth. So it looks like there is a very strong relationship in these data The response times are very highly correlated across sessions. It also looks like they vary, though, in terms of the strength of the correlation. It looks like they're a little higher for occasions that are closer together, and also a little higher the longer it goes into the study. So those are the patterns that we need to find some kind of model for the variance that fits those patterns. Here's my fit statistics. That number right there, 8229.8. 0.8. There we go. That's English. Is that good? The correct answer is that number is -2 log likelihood, otherwise known as deviance. You will hear that term in textbooks, and R uses that term for a label. It is an index of model shortness. Smaller is better. So I have no idea if that's good or not until I compare it to something else. But what I can tell you is that this is as small as it's going to get for these data, because this is the rightest possible model with respect to time. 21 parameters. And a note to the side here. This is Rimmel. It's only counting the model for the variance. So 21 comes from the 6 variances, one for each occasion, and 15 separate covariances between pairs of occasions. That's the 21. In addition to that, on the mean side, there are 6 fixed effects, 1 intercept and 5 slopes. They're not counted because in Rimmel, you can't compare -2 log likelihood between models with different fixed effects anyway. Here's the solution for the fixed effects. And then off to the side, I have written how this corresponds to the saturated means model notation. In SAS, the highest value of your grouping variable is the reference. That's session 6. So what that means is that the intercept gives me the expected response time at session 6 on average. And then here are the aforementioned 5 slopes. So these are just pairwise differences, because what's happening under the hood, these 1, 2, 3, 4, 5, these are the internal dummy codes that the program is creating for you. That is telling you how each session differs from the reference. So relative to my reference of session 6, the response time at session 1 is higher by 289 milliseconds. So they were slower to start with. So each of these is a pairwise mean difference relative to the reference session. So we typically are not interested in these pairwise mean differences. We're interested in their joint contribution as a set, which is given to us right here. So that F test with 5 degrees of freedom for the numerator, that is the joint test of all 5 slopes. So an F test more generally is a procedure by which you can lump together slopes to test their joint significance. That happens in the F test for the model in regression. That happens in the F test for the omnibus effect of a grouping variable. So this is the omnibus main effect of time in Anova language. Are there any differences across the 6 sessions? Why, yes, there are. P less than 0.05. What kind of differences are there? I don't know. 5? This doesn't tell us anything about the pattern. It tells me that on the whole, the 5 slopes are not 0. Woohoo. But it does mean there's something worth modeling. So if you are in a situation where you do this first step and the F is not significant, you may not have any change, on average at least. There may not be anything to model on average. The least squares means that are put back together again. Then if I take the intercept for session 6 and I add to it the difference to get to each subsequent session like this, that's what this table is recreating for me. So I've got the labels of the betas here out to the side. Beta 0 plus beta 1 is how I got that number. Beta 0 plus beta 2 is how I got that number, and so forth. Okay, how are we doing? So just a little bit of review, nothing new yet. But 2 questions. By what other name do you know this total answer key model when it is estimated using least squares? What is this thing called? Saturated means plus unstructured variance has a special name in least squares land. Repeated measures Anova, yes, one more word in front of it. Other one. There's 2 kinds of repeated measures Anova. There's univariate and there is other variate. Yeah, multivariate. There it is. Yes. This is MANOVA. That's what it is. Multivariate repeated measures Anova, or the multivariate approach to repeated measures Anova, or just MANOVA. That's what this is. This also has another name in SEM. So if you took SEM with me last semester, you learned this same concept as what model? Or if you took it from someone else before, you would have learned this. I can almost guarantee it. If I let each mean be what it wants, and I let all the variances and covariances be what they want, what did I call that last semester? Saturated model. H-O or H1? Oh, we got both. Now, do you remember the mnemonic? You are the hoe. This is the H1. It's a joke. I had a student once ask me when she was looking at her output from M+, in which there are likelihoods that are labeled HO and H1. She looked up and said, "Am I the hoe?" And so I had to say, yes, Lindsay, you were the hoe, which means the H1 is the saturated model. So, yes, H1. So, trying to help you make connections across all of these different ideas here. This is the goal. What makes this multivariate in Anova land? It makes it multivariate because rather than trying to estimate one variance across all of the repeated measures and say part of it's between and part of it's within, we're treating the repeated measures as if they're totally separate variables. So it's kind of a semantic distinction, but think of it like the context in which MANOVA would be used. Let's say that you are doing a study about changes in depression over time, and you might collect multiple different measures of depression, like the BDI and the CESD. See, I'm a psychologist again. Like all these letter soup, right? There's all these different ways of measuring depression, and you might have a question about whether change in depression is indexed differently according to these different tests. Well, in that context, you would have like a BDI variance, a CESD variance, a depression measure number 3 variance. You're treating them as like totally separate variables, in which case, of course, they should each have their own mean and variance. Why? They're on different scales. Why would you do anything else? So this is ignoring the fact that it's repeated measurements of the same variable and just treating them like it's 6 different outcomes. So it's multivariate. And by the way, this is exactly what I would do if I had pre-test, post-test data. I let the pre-test have a variance, I let the post-test have a variance, they got a covariance, it's fine, it's done. So I would treat it as a multivariate model in that regard. If you only have 2 occasions, you can't do any of the cool shit that we have yet to talk about. Okay. So this is MANOVA, this is the saturated H1 model in SEM. Now here's the other alternative, the worst model. So everything that we're going to look at is somewhere between these 2 extremes. Empty means random intercept. So in this case, time is not in the model at all. I only have a fixed intercept in my model. I only have a random intercept and a residual in my model for the variance. So this is my compound symmetry model. So random intercept only, type equals VC on the repeated line is a diagonal structure with just residual variance at each occasion that's the same and no covariance whatsoever. So in Stata, that happens by default because Stata has a random intercept by default. The VC structure is known as independent. And in R, I am switching to Elmer because I have a random intercept in my model right here. I have a fixed intercept in my model right here, and R as a VC structure is all that Elmer allows. And then asking for all of the various matrices to be printed, just as a pedagogical tool. So this is what R looks like. So this model tries to partition the total variance and covariance over time into two sources. R holds the variance of the level 1 residuals. So this is a empty means model with only a random intercept. That means the residuals are relative to the same flat line for everybody. So the residual variance at any one occasion is predicted to be 44,900. Again, we're in milliseconds. And the empty spaces here mean that the model predicts these residuals are uncorrelated. Then I've got my random intercept variance in G. So the variance across people in the deviation of their person mean from the grand mean, the variance of my random intercepts, that much is 200,883. And where the diagonal on the V matrix, the put back together again marginal predicted variance covariance matrix, it's the 4490 at level 1 plus the 200 and some odd at level 2 gets to me to the total right here. So V is compound symmetry when all is said and done. The covariance that comes only from the random intercept variance is converted to a correlation right here. And as I note, this correlation has a special name. This is my intraclass correlation. So you can interpret that number, 0.82, in two different ways. You can think of it as a proportion. So 82% of my variance in response time is what? This is a finger question. Level 2 or level 1? %82 of my variance is what level? Level 2 or level 1? It is 2. Very good. It's between persons in the mean differences, level 2. That means that, trying to do the math in my head, 18% is level 1. Another way to look at this is that 0.82 is the average correlation of residuals from the same person. So the fact that all of these correlations are 0.82 is sort of, that's why, that's the interpretation that it's given. So another way of saying this is that this study is an 82% waste of time because this is the variance that I would have had in measuring them once. This is cross-sectional. Some people are faster than others, the end variance. So this is a crappy model. We know that. It says there is no change. It says the variance across people is the same. We know that's not true, but it's a benchmark. It's a benchmark that we can use to see if things that we add improve the model. And it's also intraclass correlation just as a descriptive statistic is an expected thing that you should provide in any kind of longitudinal analysis for any variable that's measured over time. So the two parameters in the model for the variance are summarized right here. This is a test that is automatically provided for you that is only useful in this one instance. This is a comparison of the -2 log likelihood that would have been for the model without a random intercept. So against an E-only regression model. And so this is saying that the intraclass correlation is significant. The test statistic is 691. This is also provided in Stata by default as well. I don't think it is in R, but maybe there's a way to ask for it. But this is the only instance in which it would be useful. Number of parameters in the model is still just 2 because Rimmel doesn't keep track of fixed effects. And then here's my fixed intercept, gamma 0, 0. So that's where I got this blue line from and where I got this red line from. So worst model is empty means random intercept. Best model, saturated means unstructured. And we'll explore lots of possibilities of intermediate choices. Okay, questions? Is this helpful to go back over things again? Okay, big nods. All right, good. At least it's not harmful, right? Like, okay to helpful is the range I'm going for. And everybody did finish their homework, by the way, so I will be weaving in sort of answers to that as we go through this thing. All right, then if no one wants to have any more questions, I will say thanks for showing up. Hope to see you Thursday. Let me know if you need anything. Otherwise, take care.